Hello, everyone. Now let's talk about inference. My name is Maksim. I'm part of NVIDIA effort called Dynamo. And what we are doing, we are focusing on data center scale inference optimizations. Production scale inference is challenging. So today we are serving models that can contain trillions of parameters. They generate enormous amount of tokens, especially in thinking mode. They consume a lot of tokens when you send them huge prompts and contexts. For production grade system, you want a lot of things. You want them to be responsive, right? You don't want like a model just wait for a long time until it generates the first token, right? You want to make sure that you can serve multiple users at the same time, so it provides high throughput. You want it to be intelligent in the sense that there is no performance degradations or accuracy degradations if compared to the train model checkpoint due to quantization or other different reasons. You want it to be cost effective and energy efficient. So there is so many different things that you need to take into consideration when you're running production grade inference workloads. That's exactly what we are trying to focus on in Dynamo, how we can serve LLMs at data center scale. So let's zoom into what is inference. And essentially, inference consists of two different workloads. Prefill, when you take your prompt and you process it, and then decode, when you start generating token by token. And an interesting observation here is that these two different phases, they have different bottlenecks. Prefill is typically compute bound, while decode is memory bandwidth bound. And the main reason being is that for every new token that you generate, you need to pull full model weights from HBM into your GPU cores. So the way we've been running inference so far was collocating these two phases on the same GPU, on the same host and node. But what happens in practice, especially when you're running multiple users, and you want to make sure you have continuous batching, which means like you're in the process of generating tokens. When a new request comes in, you need to add it to the in-flight batch, which means you need to run this prefill phase. And during that time, generation is paused for all the other in-flight requests. So people have been trying to address this problem, applying different techniques such as chunk prefill, but a better solution could be just apply disaggregation. So disaggregate these two phases and make them run independently. And the way you can do that is you allocate certain amount of GPU resources to just run prefill. So you process your prompt, you compute KV cache, then you transfer that KV cache to the decode nodes that only run decode. So by applying this trick, this type of optimization, you can achieve sometimes significant throughput increase. So this disaggregation is just one of the optimizations you might think of when you're talking about data center scale inference. There is other things that you should probably consider. Scheduling, how you can route requests between different worker replicas. Memory management, how you deal with KV cache management, avoiding its recomputation, how you transfer data between multiple nodes in your cluster, etc. So in NVIDIA Dynamo, we're trying to apply all possible known techniques. And the first one that I already briefly described is disaggregated serving. When you run prefill on one set of GPUs and decode on another set of GPUs, and that way you can achieve significant throughput increase. It's very important to take into consideration your target GPU architecture. Just an example, when we were optimizing DeepSeek R1 model for Blackwell and compared that to Hopper, applying different optimization techniques, we were able to achieve 15x throughput increase in performance. So here on this chart, you can see x-axis is interactivity, which means like how fast you can generate tokens. It's measured in tokens per second per user. On the y-axis, you have throughput normalized by GPU, so how many tokens you can generate per second per GPU. And there is a trade-off. This is like a typical trade-off. You can be super interactive, like generating tokens super fast, but you need to spend more GPU resources. And usually you want to find a sweet spot on this curve and decide what is your configuration that you want to deploy. Another interesting observation in LLM inference workloads is that a lot of requests, they share part of the prompt, right? Just an example, you might have seen some leaked system prompts from OpenAI GPT models or Anthropic models. They contain instructions, what model is supposed to say or do and what is not supposed to do. And those system prompts, they are constant. They are there for every single request. And it doesn't make sense to recompute KV cache for this chunk of the data. Instead, you want to reuse it. Another great example could be you're trying to reason about certain data set, right? You're sending some documents to large language models asking different questions. So the context remains the same. It's just like the set of documents, but questions are different. So one interesting optimization you can apply here is that reuse computed KV cache. For example, when a new request comes in, a component called router contains information about all the prefixes that have been cached on all the workers. And it can decide which worker contains this specific prefix so that it makes sense to send it there and save a lot of, avoid a lot of recomputation. It's called KV aware router. So router takes into consideration which prefixes are cached where, in addition to overall load on any specific worker replica. If it's KV cache, super huge, it's running out of memory. So it's balancing between these two kind of criteria. So when you're running things in production, your traffic patterns might change. And in Dynamo, we have a component called SLO-based planner. Essentially, the main idea is that you want your workload to guarantee certain service level objectives. You want your time to first token to be reasonably low. You want your inter-token latency to be also reasonably low. And you want to maintain these characteristics over time. And what SLO-based planner does, it subscribes to different metrics emitted by workers and makes autoscaling decisions based on those metrics. For example, initially it can decide to assign n number of GPUs to Decode and m number of GPUs to Prefill, but as time goes on, we start seeing that Prefill becomes the bottleneck. It cannot keep up with the number of requests, and Prefill consumes a lot of time, while Decode workers, they just waste their resources waiting for Prefill to complete. So in that case, Planner can rebalance GPUs across these two categories of workers and assign more GPUs to Prefill. In a while, it might happen that now Decode becomes the bottleneck. Again, based on the metrics, Planner can make another rebalancing decisions and assign more GPUs to Decode worker and less to Prefill. So the main idea is to observe real-time metrics and make autoscaling decision accordingly. We have talked about the idea of reusing KV cache. There is one interesting challenge there. Amount of GPU memory is limited. You cannot store all KV caches computed so far in GPU memory. You need to free it from time to time. And just an interesting idea could be, let's just take these KV caches pre-computed and offload them to CPU memory. And when it fills up to local disk, or even we can go further and offload it to some remote storage. And whenever we hit that prefix again, we can pull it from that storage back into HBM and keep processing. So for that specific purpose, we developed a component called KV Block Manager that is responsible exactly for that. Managing KV caches, offloading them to different tiers of storage and pulling them back when needed. When we are talking about serving production-grade inference, typically you want to use Kubernetes for that. That's where most of the production-grade workloads are being served. In Kubernetes, you have a number of challenges. So first of all, you want to make sure that whenever you're deciding to assign hardware to your workers, you are topology aware. In this specific case, you want to make sure that Prefill and Decode workers, they have high throughput communication, interconnect between each other, so they can send KV cache relatively quickly, because otherwise it will become bottleneck and you might see certain hit on the performance. You want to make sure whenever you're scheduling, you schedule things so that at least, so in this case we have front-end, Prefill, and Decode components. We need to make sure that at least one component, one replica for each component is getting started. The cluster has enough GPUs and CPU resources and nodes to schedule it. Otherwise, it will just be in a hung state where you have one front-end, one Prefill, and there is no GPU capacity for Decode, and you can get stuck forever. In Kubernetes, it's called gang scheduling problem, so you want to schedule everything or nothing. So in order to solve that problem in Kubernetes, we developed a bunch of operators. Topology-aware scheduling and gang scheduling is provided by Grove, and we have Dynamo operator that essentially allows you to easily transition from local testing to data center scale. There is so many degrees of freedom when you try to decide what is the optimal configuration. So imagine you have a Prefill Decode disaggregation, and you can choose many different tensor parallelism for your Prefill worker, for your Decode worker. You can choose between different ratio between number of GPUs you dedicate to Prefill or Decode. So this is like a problem that we want to guide somehow customers. We want to remove the guesswork from disaggregated serving setup. And AIConfigurator is the tool, which is part of Dynamo Suite, that solves exactly that problem. Essentially, what it does, it takes as an input your target model architecture. In this case, it's Qwen32B. Your GPU budget, how many GPUs you can afford to serve it. Your projected input sequence length and output sequence length, and then it can generate this Pareto curve. So we see here internal kind of mode, two curves, one for aggregated mode, one for disaggregated mode, and essentially the axes here are, X is tokens per second per user, the interactivity, the same plot that we saw before, and Y is throughput per second per GPU. And then you can choose a point on this plot, and AIConfigurator will give you the exact configuration that you need to render and apply to your Kubernetes cluster. And in this specific case, you can see that by just applying disaggregation, let's say we take a point at 90 tokens per second per user, you might get up to 3x improvement in throughput. So this tool is available in both CLI and the web-based user interface. And it solves a very important problem. Given my requirements, what is the configuration? And it tells you exactly that. So in Dynamo, we are exposing different metrics. So monitoring stack is pretty mature. It's compatible with Prometheus and Grafana. It works with them out of the box. You can easily extend those metrics and add some custom stuff that you need if you want to. And here's the recap of the Dynamo architecture and the ecosystem in general. So essentially, the top, going from top to bottom, it has an API server, exposes compatible with OpenAI API. Router is KV aware, so it makes routing decisions based on what worker contains which KV cache. There is disaggregating serving mode enabled if you want to. So when the inference is split into Prefill and Decode. Data transfer is happening with the help of the Nixel library, which is like low latency communication library, which is part of Dynamo Suite. SLO-based planner is constantly observing metrics and making autoscaling decisions and rebalancing or reshuffling GPU resources between Prefill and Decode. For Kubernetes-related stuff like topology-aware scheduling, gang scheduling, there is Growth and Dynamo Operator. And KV Cache Manager responsible for KV Cache offloading. So Dynamo is fully open source. You can get it from GitHub, built from source, or use pre-built containers and like other artifacts. There is available roadmap, tutorials, technical documentation, getting starting guides, and everything else. There is a bunch of pre-optimized recipes for the most popular models like Llama, GPDOSS, DeepSeek-R1, and others, targeting specific GPUs. So feel free to try it out, play with this. And if you are interested in data scale inference optimizations, this is the right thing to look into. Thank you.